Thank you very much, Sebastian, and thank you for inviting me. Okay, my name is Eiji Saitoh from Tohoku University, Japan. In my talk, I'd like to show how these elementary excitations contribute to the Seebeck effect, spin waves, and spinons in spin liquid, and phonons. First, I'd like to give a short introduction to the basic concept of spin pumping and spin Seebeck effect, and I'll mention the spin current in antiferromagnetic, and mention the spin Seebeck effect in spin liquid, and finally I'll mention the phonon in the spin Seebeck effect. Okay, so first the introduction. Okay, the spin pumping is the generation of spin current from the magnetization precession motion like this. This is the ferromagnet, and this part is conductor. And from the magnetization cyclic motion, a pure spin current is generated. This is the spin pumping. This is the simplest implementation for the spin pumping under inverse spin Hall effect. Basically, this system is a ferromagnetic layer and conductor layer, like EEC and Pratchett layer system. And we apply to microwave like this, and microwave induce magnetization precession motion. And from this magnetization precession motion, the spin current is injected into the conductor. And this spin current is converted into electromotive force via the inverse spin Hall effect. Okay, so this is the fundamental configuration for spin current generation and measurement. Okay, so spin Seebeck effect. The simplest understanding of the spin Seebeck effect is thermal spin pumping. When a part of the sample is heated, this heat can make induce the magnetization fluctuation motion, and this magnetization fluctuation precession can inject a spin current into the conductor. And this spin current is converted into electromotive force via the spin Hall effect. So this is the simplest configuration. So the EEC Pratchett barrier system, and we apply heat current to the sample, and with applying a heat current, voltage appear like this. Okay, so this is called a spin Seebeck effect. So this is the magnetic field dependence of spin Seebeck effect. When we reverse the sign of the magnetic field, the sign of voltage also reverse like this. So what if we apply much stronger magnetic field to this system? We found that at very low temperature, spin Seebeck effect signal is rather separate like this. So we apply the 14 Tesla at 2 Kelvin in the bulk X sample, and we found a spin Seebeck effect is completely separate like this. This shows that the spin Seebeck effect is a thermally induced spin pumping, because a very strong field at low temperature suppress the magnetization fluctuation, because the field open a gap in the spin wave sector. So this shows that a spin Seebeck effect is a thermally induced spin pumping. Okay, so spin Seebeck effect has been reported a lot of systems, a lot of combination of magnetic materials and conductors. So spin Seebeck effect is a universal phenomenon in magnetic materials.
Just ask a quick question on the previous slide.
Okay.
Like at zero field, why is the jump so sharp? You know, like magnetization should be some more gentle, like.
Oh, here.
Yeah. Why
Here.
It's completely vertical.
Oh, this is the switching of the magnetization. The hysteresis.
Okay, so it's so sharp. Okay.
Yeah, so sharp. Okay. So this is the So look at the scale. This field is very strong, 40 Tesla. Very strong field. So it looks very sharp in this scale. Okay, so this is the development of spin-Seebeck effect and efficiency since its discovery. When we found the spin-Seebeck effect many years ago, the efficiency was very, very bad. But in about 6 years, it has been improved a lot, about 400 times in terms of ZT factor. Now it is as good as N-type silicon. Okay, so let's move to the spin-Seebeck spin current in antiferromagnet. As I showed you, spin pumping is related to magnetization motion at a junction. So it should be related to the magnetic susceptibility at the interface. So spin pumping may measure magnetic susceptibility of a very thin film by putting this sample into the spin pumping system like this. Since the spin pumping is very sensitive to the magnetic susceptibility here, so we inserted cobalt oxide, cobalt O. Cobalt oxide exhibit antiferromagnetic transition. So we made a total sample of each cobalt oxide and platinum. And we observed the spin pumping across this layer. Each layer is for spin injection, and this layer is for as sample, and this layer is used for the measurement of spin current. Okay, so spin current conduction in antiferromagnetic material has been confirmed by Ohio University group and the Kyoto University group. Ono-san, the next speaker. Okay, so let's move on to the result. So this is the spin pumping as a function of our temperature without cobalt oxide layer. The temperature dependency is monotonous. Nothing happens. So we inserted cobalt oxide. Then a sharp peak structure appears, and this peak temperature coincides with the narrow temperature of cobalt oxide layer. In fact, by changing the narrow temperature, by changing the thickness of the cobalt oxide layer, the peak temperature is observed to shift in response to the change in the narrow temperature of the cobalt layer. And we found that the temperature dependence is quite similar to the temperature dependence of the magnetic susceptibility. So this data shows that the spin current is conductive at a narrow temperature, reflecting the enhancement of the magnetic susceptibility. Susceptibility enhancement means that magnetization deformation becomes soft, which means that the spin current is readily be injected. So the spin current is easily to be injected at a narrow temperature. Okay. Similar enhancement at a narrow temperature was observed in the spin-Seebeck effect. This is a spin-Seebeck effect for the spin to the barrier system to which the nickel ore is put. And we observed the enhancement of spin-Seebeck effect at a narrow temperature like this. So this means that the spin current enhancement at a narrow temperature is a kind of a universal feature.
Andrew, I have a question. So now this hysteresis is not as sharp as before. Is that the scale is different or nickel oxide introduced?
Oh, this is just 300. Scale is very different.
Okay. Excuse me. Is the scale is larger than sample without nickel?
No.
No.
Yeah. Okay. Okay, so this is antiferromagnetic spin current. So I'd like to move on to spin-on-spin Seebeck effect in the spin liquid. Okay, spinon is an elementary excitation in a quantum liquid set. So first, I'd like to compare spin wave and the spinon in the spin Seebeck effect. First of all, for the spin Seebeck effect measurement, we have to apply magnetic field to align the magnetization like this, ferromagnetic case and antiferromagnetic case. Then we apply, we have to apply heat to bring fluctuation into this system. In the case of ferromagnetic material, the ground state is fully spin polarized order state. So when fluctuation is brought into the system, this fluctuation should reduce this magnetization. So what the fluctuation has is negative spin polarization, which is carried by spin waves. So spin wave has negative spin polarization, and temperature dependence of magnetization at the field has negative slope like this. This is kind of a ground set fully polarized, and by putting fluctuation to the system, this magnetization is suppressed. This is carried by spin wave. Okay, this is a ferromagnetic case. The parametric case is something similar. On the other hand, in a certain type of spin liquid, ground state has strong singlet correlation. So when the fluctuation is brought into this system, the fluctuation can break this singlet correlation in part, and magnetization along the field appears. So what the fluctuation has is positive spin polarization, which is carried by spinons. So this ground set is a singlet correlation, and by applying the fluctuation, magnetization can appear like this. So the magnetization under a field as a function of temperature has a positive slope like this. So
I'm saying that zero temperature magnetization is zero. Like in linear response?
The ideal material, no, they're finite. Okay, so, but unfortunately, in many of the spin liquids system has very short correlation. But among them, there is a good system. This is a Luttinger liquid in the one-dimensional spin chain. In this system may exhibit a long-range spin current because of the long-range spin correlation due to the critical fluctuation. So this is a good material, and it is realized in one-dimensional half-spin chains. The elementary excitation in this state is, of course, spinon. This material is a paramagnetic system, so there is no magnetic ordering. Nevertheless, collective excitation, soliton type collective excitation may appear. This is a spinon. Its spin excitation spectrum is like this. This is a wave vector and frequency, and this spin excitation spectrum is confounded by neutron scattering. Okay, spinon is a spin half a fractional excitation and gapless, robust against the field. And magnetic susceptibility as a function of temperature have positive slope like this in this temperature range, which means that spin polarization of spinon is positive. Okay, famous material in which spinon excitation is well established is strontium copper oxide 213. This is high TC cuprate related materials, in which spin chain, half spin chain is formed along the b-axis like this, and the spin chains are well separated like this. And in this material, spinon excitation is very confounded by neutron scattering like this, and the thermal conductivity as a function of temperature exhibit so-called spinon peak like this in the very pure material, like 5N material. So this means that spinon conduction is predominant in this temperature range. We measure the spinon spin Seebeck effect in this material by putting platinum on the top of the strontium copper oxide 213 material. The chain of spin chain direction is like this. So we put a platinum perpendicular to the spin chain like this. And we apply heat current along the spin chain. And we measure the spin Seebeck effect. when a spin current injected from this spin chain to this conductor, we can measure this spin current in terms of the spin Hall effect here. Okay, this measurement was done by Hirobe-kun, and theory was made by Sato-san. He doesn't like showing his pictures. Okay, so this is a result. This is a result for this sample without spin chains. So just platinum field. This is the field dependence and temperature dependence. So what is observed is a normalness effect of platinum. We can see that the sign of the normalness effect is positive, which is as the same sign as the spin Seebeck effect from Eck. So this is a well-known fact. So the spin Seebeck effect, the ordinary ness effect of this platinum is same as the Eck system. Okay, so we put a spin chain to this system. So we put the strontium copper oxide 213 to this system. Around the room temperature, like this, the sign of the spin Seebeck effect is positive, same as the sign of Eck platinum barrier system. On the other hand, by decreasing the temperature, the sign of the voltage is reversed like this, and a very strong negative signal appears here. And this shows that at low temperature on the spin chain, the voltage component with negative sign appears in addition to the normalness effect of platinum. So this is consistent with the spin-on-spin Seebeck effect prediction. In fact, this signal is spin Seebeck effect because when replace this platinum layer with tungsten, the sign of the spin Seebeck effect, a sign of this voltage is reversed like this. So this shows that this voltage is due to the spin current. And when we apply heat current perpendicular to the spin chain, so we put a platinum layer parallel to the spin chain, and we apply the heat current perpendicular to the spin chain. Then the voltage signal is not observed. So this data shows that this voltage is due to the spin current, induced along the spin chain. And it is caused by heat current, and the sign is negative. So it is consistent with the scenario of spin-on-spin Seebeck effect. In fact, what is observed is consistent with the calculation for the spin-on-spin Seebeck effect, which is based on the expanded Bostonization method under linear response theory written by Sato-san. So this calculation reproduces a negative spin Seebeck effect proportion to the field. So this is a ferromagnetic case, a spin wave case, and this is a spin-on case. So for the details of calculation, please refer to this site. Okay, so of course, in the antiferromagnetic phase, actually this material exhibited antiferromagnetic transition at very low temperature, 5K. The negative component is completely disappears. Then the positive spin wave spin Seebeck effect appears. So this part is spin-on-spin Seebeck effect. Okay, so let's move to the final part. This is the phonon. Okay, so I'll mention the phonons in the spin Seebeck effect. Okay, so the data was already shown by Bauer sensei yesterday. So okay, so this is the spin Seebeck effect in a sputtered Eck platinum barrier system. this is spin-Seebeck effect, voltage, and this is a field. So we can see the sharp peak here. So we thought this was just noise. But after some examination, we found this is a real signal, kind of authentic signal, because this data is completely reproducible, and the peak appears in all the measurement systems which we have. So different electromagnet and many voltmeters. So we conclude that this is a kind of real signal. And we found that this peak is enhancement of spin-Seebeck effect, because this peak height is proportional to the temperature gradient. So when switching off the temperature gradient, this voltage peak is not observed. So this means that this peak is not a noise, not a noise. Then one of my wonderful students, Mr. Kikawa, he noticed that this peak field coincides with the point touching condition between phonon and spin wave dispersion. So this is spin wave, and this is phonon dispersion, frequency and wave vector. So when we apply the field to this system, spin wave dispersion should shift to high frequencies, but phonon does not move. So when we apply the field, the number of intersection points between spin wave and the phonon changes from 2 to 1, and at last there is no intersections. This condition is called the point touching condition. So by using material parameter of Eich, like spin stiffness constant and sound velocity, he estimated that this point touching condition should be around 2.6 Tesla, which coincide with this field. So this data suggests that a phonon spin wave interaction might change the spin-Seebeck effect. So near this intersection point, phonon spin wave hybridization state should be formed like this. So how does spin wave phonon hybridization affect the spin-Seebeck effect? So we started collaboration with wonderful theoreticians, Dr. Kashen and Baba Sensei and Benedetta and Professor Dewing, because they already started the calculation of the so-called magnum phonon polaron. Okay, so we started collaboration and we discussed. So what should we? Okay, so what should we do next? Here, important point. There are two acoustic phonons, TA and LA phonons. TA is like this. It's a transverse mode. LA is a longitudinal mode, and TA branch and longitudinal branch. There are two phonons. So if this intersection is what we found, there should be another intersection between the spin wave and longitudinal modes. There should be another intersection between the spin wave and the phonons. And by using material parameter of Eich, the LM phonon sound velocity and spin stiffness, we estimated that the another point touching condition should be around 9.3 Tesla. So there should be another point touching condition. So we went in hunt for another peak around this field. So this is the spin-Seebeck effect data which I showed you. So we predict there should be another point touching condition at 9.3 T. So we went to the high field range. And finally, we found there is another new peak here, 9.3 Tesla, just as the field expected for the point touching condition between LA phonon and the spin wave. And we found that this another peak is also the enhancement of spin Seebeck effect, because it is proportional to the temperature gradient, and by reversing field polarity, the sign of the peak is also reversed like this. Okay, so let's examine its temperature dependence. Oh, okay. This is the temperature dependence of the peak, the lower field peak, and this is higher field peak. With decreasing the temperature, the intensity of spin Seebeck effect is gradually suppressed. So look at the vertical axis. This is 0.4. This is 0.02. So the spin Seebeck effect intensity itself is gradually suppressed. But the peak in the lower field, at the lower field, is getting sharper like this. So like this is 50 Kelvin. The peak structure is very dim, but by lowering temperature, it is getting sharper. And at 3 Kelvin, the peak structure rather predominate the spin Seebeck effect feature. Okay, lower temperature and higher temperature and lower temperature. Okay. On the other hand, as for the higher field peak, this intensity is gradually suppressed at lower temperature. This is a relative strength of the spin Seebeck effect peak at lower field and higher field. So the higher field intensity is rather suppressed below this temperature. So this temperature scale of the peak suppression is comparable to the frequency of this intersection between the phonon and the spin wave of an LA phonon. So this suppression suggests that the thermal excitation of spin wave and phonon around this is suppressed below this temperature scale, and that the peak structure, which reflects this intersection, is suppressed. Like this. This is the range of thermal fluctuation. LA phonon intersection is out of range of this fluctuation, but TF phonon intersection is within the range of this thermal fluctuation. So this intersection effect is suppressed at very low temperature. Okay, so owing to the sharp structure at low temperatures, we can get some information from the spectral shape. This is a magnified view around the peak structure at lower field peak. In this field range, the number of intersection points is 2, and it is 1 at this point, and there are no intersections in this field range. So this data shows that spin Seebeck effect intensity is smallest when there is no intersections, and it is maximized at a point touching condition, and it is intermediate when there is a two intersection points. So which suggests that the spin Seebeck effect intensity reflects the number of intersections between the spin wave and phonon dispersions. In fact, this spectral shape is well reproduced by a calculation. This is a calculation done by the Kashen and the Bauer sensei and the Dewey sensei and the Benedetta. And this is a calculation, and this is what we measured. And in this calculation, some spin flow was calculated using a semi-classical framework in which the magnetic coupling is taken into consideration. And this theory showed that spin wave flow is rather enhanced via the hybridization with phonon when the lifetime of phonon is greater than the lifetime of spin waves. And at the point touching condition, for this spin wave enhancement effect is maximized because of the maximum phase space volume near this intersection. So this calculation will reproduces all the data. So we assign this peak as a Phonon-mediated enhancement of the spin Seebeck effect, and this had showed the spin Seebeck effect is enhanced via the hybridization with phonon, and this material will satisfy this condition. Okay, so this is the phonon in a spin phonon in a spin Seebeck effect. So, by the way, so what about other sample like the bulk peak? So this is the bulk spin Seebeck effect which I showed you. So can you see any peaks here? It looks like there are no peaks. I thought so too. But looking over the data again, we can see some peaks here and here. Can you see them? No, actually. So this is a magnified view. So you can see some very small peaks here. And at very low temperature, maybe you can see very small peak here and here. Of course, you can see in the magnified view like this. So even in this bulk sample, peaks are small but finite. So it is likely that this condition is very satisfied in this bulk yttrium garnet, and we showed that the bulk yttrium garnet exhibit longer lifetime of spin wave than sputtering EEC. So the theory showed that this peak amplitude is very sensitive to the lifetime of spin wave and a phonon. So this phonon peak in a spin Seebeck effect can be used to investigate the lifetime of spin wave and phonon. So this could be a new application of spin Seebeck effect.
Why is the effect so much smaller in bulk compared to, so the largest is in thin film? So.
Maybe there are due to this condition, maybe the spin wave lifetime is better than the sputtering EEC. So I think the ratio is about 100 times, is 100 in the sputtering. Maybe in the sputtered and in the bulk EEC, the lifetime of the spin wave is much longer than bulk. Yes.
And is it something you could indirectly confirm from some heat conductor?
Maybe this is the next step we have to do.
One should do sort of ultrasound attenuation. There you could something like that.
We have to apply.
So you said it's different transport regimes and the thin films and what?
Yes. Okay, so here's a summary of my talk. I showed the spin Seebeck effect for spin wave in ferromagnetic material and antiferromagnetic material. I showed a spin-on-spin Seebeck effect in spin liquid, and showed a phonon anomaly in the spin Seebeck effect. Finally, I'd like to thank the collaboration with Kikawa-san, Dr. Shiomi, and Dr. Uchida, Dr. Dajiho, and Dr. Q, and wonderful theoreticians, Gail Bauer, and Professor Dewey, and Kashen, and Benedetta, Professor Maekawa, and Masahiko Sato, and Koji Sato, and Yarasov. Thank you very much.
Thank you.